who have been involved at some stage or another in this effort. Name of the agency is back there. And so I think that if our goal is not biology, is not understanding the brain, I think we owe to ourselves a justification of why we actually need the notion of representation and what we mean by representation. And I'd like to argue that control has something to do with it. And so, I guess in the spirit of JFK, what I would like to argue is not so much that vision as a sensor is useful to control for interaction with the scene and so on and so forth, but the other way around, that control is critical to build representations. So if we weren't able to control the data acquisition process, that issue would be problematic, the building a representation. So what do I mean by representation? So I think we all agree on what the data are, right? So there's no discussion there. I think of data as images, and I think of a time series as a series of images from time 0 or minus infinity, whatever you want, up to time t, and I use the mnemonic y up to t. So this is fairly common in system identification. And I think that when we talk about tasks, that's where there's a little more disagreement. So what is a viable task? It could be as simple as binary classification, detection, is an object I said before in the image, yes or no. It could be as complex as survival, and anything in between. It could be reconstruction, it could be mating, it could be whatever you want. So I don't think that we will agree on that. So, but to me, vision is about inferring properties of the scene. And so whether it's queries or reconstruction or classification, detection, recognition, whatever you want pertaining to the scene as opposed to the image. So I will call the task in an abstract setting as C, yes?
At this level of generality where we don't know where y0 and yt are, say, vector matrices, graphs, or whatever, if you think of a task, and but you're assuming you have some knowledge, it's like a supervised situation, you assume there is some form of structure attached to those.
No. So this is data that you give me. I have no control over that. I make no assumptions. So I will want to model the data formation process, but let me come to that in a minute. So for now, this is formal notation. It's not rigorous, but it's just to set the stage for what I mean by representation. So I think we all agree on what the data is. I think we don't agree on what the task is, but I think we all agree that whatever representation is something that sits in between. So we are empiricists, so we believe that whatever we know comes from the data, whether through evolution or through our ontogenic process. And so I will call a representation with a symbol C hat, which is a function of past data. So we are at time t, we saw data up to time t, either we as individuals or we as a species. And I will call the representation in statistics, so a function of the data, and you give it a t. So actually we get C hat. Now, C hat might suggest that the representation has something to do with the scene. And presumably, a representation will be a function of the data that is useful, in some sense, to the scene. But I would like to stress that I am told by both mathematicians and philosophers that it's very important that whatever theory you develop on representation, it never requires that you acknowledge that the scene exists. Okay? So, how do we know? And so, from a philosophical perspective, I don't quite get it, but from a mathematical perspective, that means that the scene is a phenomenally complex object. You really don't know the scene other than through the measurements that are given to you. They could be cross modality, but you can only know the scene through probing functions or measurements. So I will never try, or I will try hard never to compare Xi hat with Xi. But Xi hat will have to be useful for Xi in some sense. Are you okay with that? If you're not okay, throw a snowball. Yeah.
I'm not okay.
Okay.
Why should I make a prediction theory for completely hallucinating? Just because the philosophers don't come to grips with reality.
No,
You can find some other philosophers.
You're not making prediction from hallucinated data. You are making prediction from past data about future data, and the way you validate this is not by comparing it to the scene, but by comparing to data that the scene generates.
You said Xi is a task or
Xi is, right now, Xi could be a binary variable, it could be the entire reconstruction of the scene or whatever you want. Joachim.
I'm confused. What do you mean you should not acknowledge that the scene exists?
So, so all you know about the scene is that it generates data.
But you can have the data from the scene.
You can have as many data as you want from the scene.
Oh, is that paraphrasing that the scene is an oracle and you can carry it as often as you
You can think of it that way.
Okay.
You're okay with that? Okay. So let me try to make this. Let me try to make a statement on that is independent on what your task is. Okay. So your data is your data up to T, and presumably the representation should be useful for X or informative or whatever you want to call it. Right? So now there is a pointer somewhere here, right? Is this a pointer?
Yeah.
So, if you compute the mutual information, now this is again all formal, so I don't know how to actually compute these things, but if you were able to compute these things, then the data processing inequality tells you that the mutual information between what you know and what you want is always greater than or equal than the mutual information between what you know and any deterministic or stochastic function of what you know. Okay, so in other words, by inferring a representation from the data, you can only do damage. So you can do no better than by just storing all the data. Okay? And that's true for mutual information, or it's true for risk or for control functionality. This is a very general statement that I think we all have to contend with if we want to design representations for engineering purposes. Okay? So this really begs the question of, do we really need a representation? Maybe we ought to just store all the data, and maybe Jan is right, and we don't build, we just build a genetic functional approximator and we let it figure everything out. So I think this is important, and I think this is often forgotten, especially in engineering. Yes?
Yeah, it's not missing easier, it's computation.
It's not really missing in the sense that computation comes in as a regularizer in the cost functional, but this statement still holds.
Yes, they don't always, but it's really not about whoever one is. How do you choose the trade-off between something that's perhaps less.
Let me come to that at 3/4 to this slide. Let me see if you are still unhappy with that statement. So now, there is a less than or equal sign here. So if you manage to get the equal sign, that would be called a sufficient statistic. And if you could compute that, then that would be your ideal representation. Right? Of course, there always exists a sufficient statistic is the function that gives you back the data. So it's not very interesting. You would like the minimum sufficient statistic. And if you could compute that, that would be a viable representation that doesn't violate the data processing inequality. Now, there are theorems, Pittman, York, Koopman, that says that this is very difficult to do. So it's reasonable to say that instead of trying to make these two things equal, try to make them as close as possible to each other. And as I said, you certainly want to introduce some type of complexity constraint, call it identity, whatever you want, of your representation. And so this seems to be a very reasonable thing that you might want to, a reasonable principle that you might want to use to infer representations. And this has a name. If you play around with properties of mutual information, this looks like this. And this is called the Xi hat that sits in between your data and your goal is called the information bottleneck. And this is work by Viale, Pishpi, and Pereira back from the 90s. Many of you may be familiar with that. So
Sorry, where is the cost gone now when you're minimizing?
it's hidden in here. So this is the mutual information between data, sorry, between the representation and the scene. Okay. Now, one problem with this is that the scene is here, and I said I don't really want to, I don't know how to compute things on the scene. I don't know how to put metric, let alone probabilistic structures, let alone distributions, let alone priors, let alone marginalizing things. So this is a bit problematic. But if you play again with properties of mutual information, you get something like this, and I'm hiding a few assumptions here to avoid entanglements. But basically, what this is telling you is that what you should try to do is, given your representation, which is a function of past data, that representation should be able to predict future data. Pretend that this is entropy for a second. It's not quite entropy. But so you should try to find a representation that, for a given complexity cost, tries to minimize the uncertainty of future data. Okay? So this is quite reasonable. Okay? And this is the information model.
What does like an NDL?
Well, this is more like a prediction error method argument, with the complexity cost. But I'm not saying that you should use minimal description line. Here you can use whatever you want.
No, but in general terms, it depends on what you define complexity.
Right, but this is general prediction error methods in system identification. This is except that you measure uncertainty in different ways. Now I put a script H here, which stands for the fact that I don't really care to predict future data. I care to predict the part of future data that matters to the task. And this is what this symbol stands for. And in some cases, that could be a tiny fraction of the data. Okay? And so this is what we call actionable information, in the sense that it's a complexity not of the data, but of the maximal invariant of the data portion, the nuisances you don't care about.
So, but all the quantities on that slide are expected quantities, not empirical. So in that sense,
Correct.
this H which you add is just, it's not coming out of the theory. It's your a priori bias towards simple explanation.
So what I will try to do next is I will try to instantiate these quantities for a model. Okay. So yes, the model is a prior, and yes. So the answer to your question is yes.
Sorry, maybe I just lost it. So R is some notion of what is R again?
R. What is R? Oh, this is a risk functional. If you have, instead of mutual information, you can do the same thing for a control function.
And the H, the other one is some notion of regularization.
I will yes, I will talk about this. Any other questions? Okay. So now, by the way, if this was a linear, finely dimensional Gaussian model, this would be the separation principle in systems theory, and this quantity C would be the state of the Markov splitting subspace, is the statistic that makes the past conditionally dependent on the future. Okay, so think of this as a generalization of the separation principle. And this would be, if you could compute it, would be what you store in memory. This would be your ontogenic memory. Okay. This would summarize, would be a finite complexity statistic that summarizes all the past for the purpose of predicting, not future data, you don't really care to predict the pixel values, but the part of the data that matters to the task. So this is definitely task dependent, it is model dependent, it is modality dependent, all true. Okay. Okay. Now, just a couple of, I think I can probably skip this, but to me the past includes your past memory as a species, which is encoded in the choice of tasks, in the choice of nuisance factors, in the choice of invariances, in the choice of policies, trade-offs, and so on and so forth. And so the structural priors, if you wish, and your ontogenic memory, which is what is aggregated into the representation. Now, I spoke about nuisances, and to me this is an important point because in my view, what distinguishes vision from most other data modality is that nuisance, so you have two types of variability in data. Intrinsic variability that depends on the objects you wish to say something about, or infer, and nuisance variability that has nothing to do with Fourier state, but nevertheless affects the data. And vision has the peculiarity that the latter variability floods the former. So you're literally looking for a needle in a haystack. You can, so nuisance variability can account for almost all the uncertainty or variability in the data. Now, not all nuisances are born alike. There are some that have structures that allows you to eliminate them at the outset through a constructive process that is called minimization. And then there are others that you will have to marginalize or somehow get rid of in some other standard way, max out, marginalization. And then there are others that you will have to exercise control if you want to get rid of. Okay? And that's good point. So what I would like to do is I would like to take this formal notation and make it a little more concrete by instantiating it on the simplest model I know that has all the ingredients I need. Now, unfortunately, that model is not all that simple, but I'll try to keep it as simple as I can. So here's a flow chart. This is not a hierarchy. This is not an architecture. But it sort of summarizes visually what I mean. So here's the scene. We're not philosophers, so we assume it exists. And the scene generates data. That we know. Right? You have different modalities, and you know something about these modalities. So this is not a black box. You know how electronically reduce it. Now, the data also depends on some nuisances that are aspects of the data formation process you're not interested in. And some of them have the structure of a group, so I will denote them as need. Some of them don't have a structure of a group, so I just call them need. And then everything else that you don't model, you lump it as an unstructured perturbation or unmodeled phenomena, and that comes in additive. And by construction, you assume that it's Y0 mean, homoscedastic, and statistically simple. So you generate data. Now, your task determines what part of the data is nuisance and what is not. If you want to recognize that illumination is a nuisance, viewpoint is a nuisance. If you want to navigate, viewpoint is not a nuisance. If you want to render, then reflectance is important. If you want to recognize or navigate again, reflectance is not. So you know what you care about and what you don't care about. So the system knows that. And the system is able to predict not the data, but the maximal invariant of the data relative to the nuisance factors that you can eliminate at the outset. So there are some of the nuisance that through a constructive process you can eliminate from the data. So you can obtain strict invariants that are lossless. So you get rid of that nuisance and nothing else. And so that generates, so phi hat stands for the maximal invariant statistic of this relative to whatever nuisance you choose. And the system is able to predict those. And that gives you an inner loop here that tries to, so that the discrepancy between the maximal invariance that the data generates and the ones that you predict is your information increment, your innovation process. And so that's what feeds the inference of the representation. This is the function I showed earlier, except that I'm looking at one step ahead instead of the whole future. And so this inner loop is the inference loop that, given data, tries to infer representation. Okay? Now that's only a part of the picture, because you could get the best possible algorithm to infer this representation, and this could be completely useless, because a critical condition for you to be able to infer a model or representation is sufficient excitation. And if the data is fed to you, you cannot test for sufficient excitation. Okay, so sufficient excitation is a condition that allows you to say that all the modes of the system are solicited, and that you cannot test passively. So in addition to this loop that tries to make the best out of the data you have, there's another loop that tries to get the best data you can. And so again, so this loop that goes in the opposite direction, that given the representation, tries to generate data that is as informative as possible. And so the criterion is the same, only that in the inner loop, you try to minimize the uncertainty of future data. And in the outer loop, you try to maximize the uncertainty of future data. Okay? You try to generate data that is as uncertain as possible. Okay? And so this outer loop is really critical, because otherwise you cannot guarantee that your representation has generalization properties.
Stefano, I'm confused about the box. So you have a representation psi hat, which is the quantities you need to know for performing your task that you're estimating.
No, the representation is what you use to, is what you can, so it's your memory essentially. So it's what you,
I see, okay.
so it's your state.
Now,
Some control parameters?
Some control, some decision parameters, something that affects the state of the world through the control of the data acquisition process.
so now when psi hat feeds into the nuisance box, what comes out of it? What is H?
What comes out is, so the nuisance box is H, you will see in the next slide, is the data formation model that generates not data, but invariants of the data for comparison with the ones that come from
I see.
the scene.
That's a way to obtain a prediction error.
So if you think of this in the linear Gaussian case, okay, think of this as ZUG optimal control or stochastic optimal control. So you have a common filtering here, and you have an optimal filter.
So let's suppose you didn't care at all about reflectance.
Yes. So
Would
that would,
psi hat contain anything that encodes reflectance or not?
No.
No. So
But
how do
this
you write your
box-
prediction of the scene?
so if you don't care about reflectance,
Right.
then if you, and I'm not saying you can, if you could get rid of the reflectance from the data,
Let's suppose you couldn't.
suppose you couldn't, then this box would have a way of hallucinating reflectance.
But how does it do it if it has no memory of the past?
If it has no memory of the past. So the memory of the past is all in here. And if you give me a scene that, let's say you're not interested in reflectance, so your scene has shape, for instance. I can always slap a reflectance function onto the scene to hallucinate.
Okay, suppose I'm looking at a cube, and a cube could be either Lambertian
Yes.
or made of metal. I don't care about, I just care about the edges of a cube because I'm navigating. I just
Yes.
want to know I'm docking to the cube.
Yes.
So Xi hat contains information
Shape.
about the shape of the cube.
That's it.
From frame to frame, I have no memory of whether before the image contained specular reflectance, mirror reflections, or it was matte, as in Lambertian. So how can I generate a guess of the picture H?
So you would try
The
to
shape of the
not generate images of reflectance, but you would try to generate images that are independent of whether reflectance is Lambertian or not.
And that's what I compare.
Yes.
But that's only if I can model the, if I know how to have invariance of the image. In any case, okay, so
Okay, so now this is just a picture, okay? So there are many details here in the boxes. I feel like I will never get to the end of these slides, but Joachim.
So the outer loop is exploration.
Yes.
And where in the outer loop is the task information entering?
So the task is in two spots, is in two places. So first, the task informs what the nuisance are. So depending on what you need to do with the data, some parts of it are relevant or not. So the task is structurally informs what you canonize and what you try to infer.
I mean, in the outer loop, do you make your search for more general data task dependent?
Yes, it's task dependent because the control depends on the representation, and the representation depends on the nuisances, and the nuisances are informed by the task. So this quantity here is the information bottleneck, and this quantity here, this innovation process, is what I call the actual information increment. Okay? So what I would like to do is I would like to instantiate this for, again, the simple model I know that has all the ingredients that I need. And so this is what we call the LA model. So when you think of the LA model, if you Google LA model, you get lots of things. I actually put this as a snowball to Jan LeCun because if you train your system on ImageNet, your system will never be able to tell a potential mate apart from an image of a potential mate. And that could have disastrous evolutionary consequences. And so I really don't believe in anything that is trained on IAD samples of objects from the price conditional, because to me, being able to distinguish an object from an image of an object is if you can't do that, then you're in trouble.
Someone who has a side activity in biometrics and fully aware of that one.
Exactly. So this is not the LA model that I have in mind. The one that I have in mind is the lambert-ambient model. This is I apologize, it's a bit complex, but it's the simplest I know that has the key ingredients that, in my view, for vision are scaling and occlusion. If your model or if your system cannot handle scaling and occlusion, then in my view, it's not doing vision. It's doing pattern recognition. And so when I see systems tested on, I don't mean disrespect, but let's say the NIST data set where there's no scaling and no occlusion, that doesn't tell me a whole lot. So this is the simplest model that I know that has the ingredients. So what does the model say? The model says that if you want to know how a pixel, how the image of the pixel X is generated, you assume that there is a scene that is made of, let's say, piecewise smooth, multiply connected surfaces, and these surfaces support a reflectance function. And so if you want to know the image of the pixel X, you just read out the radians of the point P. But it's modulated by some function that depends on illumination. And so if you, and of course it's unknown, and if you want to know how P relates to X, that's the geometry part of the image perception process. You take the point P, rotate it and translate it to the camera reference frame, project it, and you get the pixel X. Now, of course, you get the pixel X unless you have an occlusion. So this function pi here hides also the topology of the scene, because depending on where you are, you may see the reflectance of the point P or something that has nothing to do with it. Okay? So this is the simplest model I know, and so in a sense, what I've been trying to do for the past few years, and I will continue to try for the next few years, is how to compute the information bottleneck for the lambert-ambient model. Okay? to approximate. Okay. So when I say scene here, just for the sake of example, I mean reflectance, but since I'm not modeling illumination here, okay, that's possible, but that would increase the complexity significantly. You can think of this as reflectance or radiance or albedo, because there's no illumination anyway, and shape. This is three-dimensional shape, not shape. So this is what I mean by the scene. By the scene, of course, you could be a binary classifier on shape or reflectance. And then the group nuisances are your vantage point, which is a trajectory on the Euclidean group, and illumination, which here I'm modeling as monotonic continuous transformations of the range of the image, contrast transformations. The very simplest you can conceive of, because that's the only one I know how to handle at this stage. And then the nuisances that are not groups, of course, the unmodeled uncertainty and occlusions. Okay, so scale is hidden in here because as you move farther away from things, they can become smaller and smaller, smaller than it is. So this is the model that I have in mind. And so symbolically, I write this as the data is a function of the scene, which is you're interested in, and then the group nuisance, the non-group nuisance, and the additive nuisances. Okay, so that's what H in the previous box. So, as I said at the beginning, a representation is a function of past data. Okay, of all function of past data, you're interested in the ones that are useful in some sense, and so the information bottleneck formalizes that. So they're useful in the sense of maximizing the mutual information between the data and the task, subject to complexity constraint. So, and given some data, you can do the best possible job, and then may or may not be good enough. Okay, so for instance, if we give you only one image, I can build a representation from it, but it will not be very good. So how do I know that the representation is good? Well, from a representation, you can hallucinate, again, not data, but data modular nuisances. And so call this the light field of Xi. Okay, in the sense that these are data generated or pseudo data generated by this. So if your representation can generate all the data that the true scene can generate, this is of course an asymptotic concept, then your representation is complete. Okay? Really, you cannot ask for more. Of course, you will never know whether this is comparable to this. In fact, it's not. They live in completely different spaces. This is a function of past data, always finite dimensional. This is in general infinite dimensional. But you don't really care ever to this is, in a sense, the way in which you compare the scene with the representation. It's only through the data they generate. Okay? So this is what I call a minimal sufficient statistic of a complete representation is in general what I call a complete representation. Okay? So that's really the ultimate goal if you're building representations, in the sense that you couldn't do better than that. So a few names that I use. So if you measure the complexity, however you want, whatever, not of the data, but of the maximally variate of the data, quotient, and nuisances, that is what I call actual information. It's the complexity of the part of the data you care. And the complexity of a minimal sufficient statistic of a complete representation is the complete information. You cannot do better than that. And in general, there's a difference. There's a gap. Okay? So what I would like to argue here is that this gap cannot be closed if you are a passive user of data. Data is given to you. You can do the best job possible, but if there is a gap, if you are a passive user of data, you cannot close this gap. So that requires active control of the data formation process, of the sensing process. Now, small aside, there are cases when the gap is zero. Okay? So for instance, if there are no invertible nuisances and there is no noise, obviously this is a very idealistic case, and all that happens to your data is that there is a group acting on it that you don't know. It could be an infinite dimensional group. Then the gap is zero. Okay? For instance, if everything that happens to your image is contrast transformations, then you can replace the image with the geometry that occurs or the normal field, and you have removed contrast transformations and nothing else. So you haven't lost any information. You've just removed contrast transformations. That's assuming that you're not interested in contrast, of course. So even if you have viewpoint changes and contrast transformations, you can show that you can construct a statistic that is invariant to the group closure of important diffeomorphisms, which are transformation induced by a change of viewpoint away from occlusions and contrast. This is called an attributed ring tree. And this is all that's left of the images after you remove the effects of viewpoint and contrast. And this is supported on a zero measure set of the data, which means that it's a thin set. So here's a case when you've thrown away almost all the data, and yet you've lost no information. Again, you've lost no information relative to a task that requires a bias from the point of view. Okay? So this is interesting to me because this means that you can have a symbolization process, a discretization process that is lossless. Of course, not lossless for the purpose of recreating the data. You cannot do that. But lossless for the purpose of any task that requires invariance to viewpoint and contrast. Okay. Of course, and just a couple of words on how you actually build this. So the way you build this is you generate functionals of the set of images and a group that you choose. Could be infinite dimensional, could be as simple as translations. And then you design these functions to have two properties. One is that the zero-level set of the gradient have to have locally isolated extrema, so as to be Morse in sense. So through the this establishes G as a function of I through the implicit function theorem. And the second is that this local extremo, which is a canonical representative, co-varies with a group. So if you transform the image, that is equivalent to transforming the canonical element. So if you can do that, then automatically you have an invariant. So you just put the data into the reference frame determined by the covariant detector, you have an invariant descriptor to that group. Okay, so that can be done so long as you have groups. Okay, now, and here are examples of covariant detector invariant descriptors. So a translation covariant detector is Alice Corner. It's not a good one for reasons that I won't get into it. Slightly better one, Laplacian of Gaussian. Even better one, Hessian of Gaussian. This has some nice properties. You can think of it as a solution of the Motion-Ampere equation. There are simplifications of it you can do and other things. So in other words, what people are doing are already related to this. Now, this is a point that I think I've also seen in many of Tommy's papers, that really dealing with nuisances is the difficult part of vision, in my view. And so Tommy has experiments that illustrate that. But you can think of also this theorem as illustrating that in the sense that this raises issues of learnability and data sets, in the sense that if almost all the complexity in your data has to do with stuff that has nothing to do with what you're interested in, then your generic functional approximator will spend almost all of its energy trying to get rid of that before you can even start to learn about what you're interested in. Now, I have no problem with that happening, but that will likely happen over an evolutionary time scale, not at the ontogenic level. So it will not, I don't need to rediscover that there are occlusions, that there's scale, and so on and so forth every time I turn on my algorithm. That we know, and that is what, in my view, is tricky. Okay? So now, canonization is a constructive process to get rid of nuisance that works so long as you have a group. Bad news. In vision, yes?
But what if it takes half of your genome to encode all of those prior information for it so that you're ready for it properly, and that you can run it in a few minutes?
That's
takes
possible.
running in a few minutes, right?
So I'm saying that that's hard to learn that, and so if you can do without relearning it every time, that would make sense to me. But I don't know how biology encodes it, so I don't know how. Your point is good. No, so now the construction is nice mathematically and all that, but the problem is that because you have non-group nuisances, the moment you combine them, the combination is of the composition is not a group, and that the whole construction falls apart. Okay, and that's really where control comes in, because the invertibility of a nuisance depends on the control authority you have of the sensing process. Okay, if I'm a passive user, I'm here, and you give me images and something is occluded, that's it. There's nothing I can do to it. But if something is occluded and I can move, then occlusions are invertible. I just move around them. Scale is invertible. If something is too far, I can just move closer. And even noise, if you believe in the law of large number, you just stay put an average, and sooner or later you'll make it as small as you want. Right? So this, to me, is very important, and in fact, it's an old idea. I had forgotten about Gibson after reading about it some 20 years ago, but after going through this exercise, I was reminded, well, it sounds familiar, and in fact, many of these ideas were in Gibson. Okay, so I'm going to come to close to the end of my talk, so I want to give you kind of a summary of the two types of activities that I'm engaged in. So, in a sense, if you think of the information bottleneck as sort of a separation principle, then two questions arise. One is, how do you build the best possible representation given the data you have? Okay, so that's the inner loop. And so there's a procedure for doing that, and I will not have time to go into it, but it has to do with dealing with the groups that you can canonize and marginalizing the rest. And then, given that representation, how do you get the best data you can? And this is a planning or an exploration of the control problem. So in a sense, one is to get the best representation given past data, and one is to get best future data given the representation. Yes?
Are you doing anything more than just asserting that action is the cure for getting rid of these variables? I mean, it seems like
probably not.
Sorry?
Probably not. But
I mean, like lighting seems like a hard variable to get rid of by action.
lighting?
Yeah.
Fair enough. For instance, if I take this non-inversion object, illumination is static if I move relative to it. But for this object, I can control the illumination by moving the object relative to it, right? So to a certain extent, you can control illumination. And, but illumination is tricky, I admit it. And so everything that I've said pertains to contrast transformations, which are a very simplistic model and already complex enough to deal with. So definitely, so in my model, illumination phenomena other than contrast are lumped into the structure problem. So picture illumination with refraction, translucency, transparency, all that. You know. Okay. So I won't have time to get into any details. I just want to give you a snapshot of what's entailed here. So the fact that occlusion is important should give you a sense that, and by the way, you can design descriptors here that have the property of being best relative to a chosen class of classifiers. Now, I have the video here, the demo here, that I was trying to beam to, because I cannot show you the screen. I have an app that's supposed to mirror my screen, but it didn't work. So I'll show it to you here. But basically, what you see here are think of them as the receptive fields of the covariant detector functionals that can establish short-term correspondence, so through tracking. And once you click, you're learning a representation based on this. And the icon here showed you that you have redetected it. And this is invariant to planar similarities, and that's encoded invariance. And everything else is in theory marginalized. This is a very, very coarse form of visualization. And so this learns and then detects and localizes objects defined as collections of these descriptors. You can think of them as also representing categories the moment you declare that two or more objects belong to the same class, and here you do it by dragging the icon of that object onto the one that you want to declare. This is the same as that. And so from this point on, this is a mixture of objects, and so you can recognize both the viewpoint and as being the same. And feel free to come back and play with it afterwards. So the important thing is here, categories of objects come after objects. So first you say, I see this chair, and then I realize, oh, it's a chair because it has certain properties. Ideally, we would like them to be functional properties. Here it's just appearance properties. Okay. So occlusion is important. So we spent a lot of time on dealing with occlusions. I will not get into it, but the nice thing about this problem is that you can frame it as you can enlarge it into a convex optimization problem. And occlusion gives you a very important topological information because it tells you that somewhere in the scene there are surfaces where I know that this point, the point that Beck projects onto this point is in front of points that Beck project here. So I know that this point is in front of this one. Of course, I know nothing about how this point is in front of this one or that one, so I don't have global ordering. But in fact, because occlusion gives you multiply connected set, you can take all of these local partial ordering information, you can bootstrap it into a global ordering information by solving a linear program. If you put an infinity norm cost on the number of depth levels, then you can also do model selection using linear programming. So this is the cost function you would like to minimize. Let's skip ahead in the interest of time. So, but the important thing is that this gives you what we call detachable objects. So in the scene, you see several detachable objects, but one notably not a detachable object. So I don't want my system to detect this as a person, okay? And so that's definitely not a detachable object. And the system, in fact, does detect the car as a detachable object, but doesn't detect the girl as a detachable object, okay? So detachable object is a layout of surfaces that are partially surrounded by the medium. And the important thing about that is that the moment you move or the object moves, that triggers occlusions. Okay? If objects are painted, so hopefully our system will be able to distinguish a potential mate from a picture of a potential mate. So evolutionary. Okay, so I've given you kind of a slight hint. So I have no idea what's inside this box. There could be, gated RBMs as far as I know. I really don't know. What I'm trying to do is I'm trying to take this type of picture with this criterion for inference of representation. I'm trying to instantiate it for the simplest model I know that has scaling and occlusion and counting. So I'm trying to see what I can say about this loop, regardless of how you actually do inference. And then the other part of the picture that we're engaged in my lab is to say something about this loop, and that's actually an even more complicated problem because this is essentially not just an infinite quantity, but you can think of it as a quantity where the state itself is a function. So it's kind of hopeless, but it turns out that in some cases, and we've been spending quite a bit of time trying to see if there are reasonable approximation of that are submodular with Andreas Krause. That hasn't pan out so far. But we do have some pieces of it. So for instance, being able to estimate ego motion is very important for that. So we have ways of integrating inertial and visual to estimate ego motion. So this is a system that operates in real time. This is UCLA up here. This is the beach. These are 30 kilometers. And you can get quite reasonable, this is now 3-year-old work, reconstruction of trajectories. And also you can get a reference of gravity gives you a very important rotational reference because that tells you it's a global reference for orientation that is useful for recognition because you don't need to canonize orientation if your objects are located. And then visibility is one of the main sources of uncertainty due to occlusions. I'm wrapping up. And so being able to plan to uncover as much as possible is one of the optimal control problems we're trying to come up with, and you can prove algorithm plans. So let me skip this and just come to my summary. So I think that if we want to design representations, I think that we have to contend with the data processing inequality. Now, if our goal is to understand what the brain does, the brain doesn't care. It has lots of constraints from biology and so on and so forth. But in engineering, I think that's important because I feel that in engineering, the standard will be higher than in human for humans. So, if you want to build an autonomous car, it's perfectly okay for people to kill people. It's accepted, surprisingly. But it's not okay for a machine to kill people. So the standard will have to be higher. And so, to a certain extent, you can construct operators that will get rid of nuisances. Unfortunately, it's not possible for all nuisances. And so the ones that you cannot will give you a gap. And to close this gap, you will need to exercise control. So I'll leave it here. This is my favorite punchline. Many of you have seen this picture already, but it's just to remind you that if you want to build representations, you ignore mobility at your own peril. These are tunicates. They are hermaphroditic predators. They live at the bottom of the sea. They feed until they find a rock they like. They stick to the rock and then eat their own brain. So, tenured organisms. I'll leave it there. Thank you. Yes.
Have you any thoughts about how you might do motion moving objects? For example, in the scene where there was one person walking, if there were two.
So, no, I mean, obviously that we need to deal with that, and that's typically not a problem. In fact, you can. So, in fact, you can deal with situations where not only you know that this has the label person, but that there are two persons and one is in front of the other. So that information comes naturally. Joachim.
Do you
Yes.
You have full access to the true probability. And the data processing inequality basically assumes that.
Well, you have a
It's a-
model of the probability distributions, and generalization will depend on how well this model matches the empirical statistics, which, of course, I have no idea at this stage.
Okay, but a lot of the regularization you need is basically to find overfits the noise. And this is coming up.
Say it again?
The main reason why you do
Yes.
regularize is you want to immunize yourself against overfits. Making up structure in the data which is not there.
There's regularization at every step of the way here, from the complexity term in the data processing inequalities, that's a regularizer,
Okay.
right? To the occlusion detection, to the detachable object detection, there's always regulation.